down. Well, it's a great honor to introduce Massimiliano Gubinelli this seminar. We usually start with a very brief introduction of the speaker. Let me mention that Massimiliano is a Hausdorff professor at the University of Bonn. He received his PhD under supervision of Caracciolo, I hope I pronounced this correctly, and was previously professor in Paris. He is known for his many very original contributions synthesizing the study of quantum fields with stochastic analysis and PDE theory, among other things. And this includes in particular his contributions to the rough path theory, eventually leading to breakthroughs in the solution theory for SPD by authors, and more recently he introduced very novel ideas to the construction of Euclidean quantum fields, such as elliptic stochastic quantization, the use of stochastic control, the use of energy estimates, etc. And I will leave it at this and hope that we'll hear more about some of these topics in this talk.
Yeah, okay, great. Thank you a lot for this introduction. Yes, so yeah, thank you, Roland. So this is the talk for today, the title of our talk. So I choose this title as a question because somehow I think really about this talk for me as an occasion to really spur some discussion about this theme which Roland mentioned, that is stochastic analysis on one side and constructive quantum field theory on the other side, which are two themes which interest me very much, especially in the last period. And yeah, for me, it's really open discussion. So don't mind to interrupt me, ask questions, and even be critical, because I really need some feedback from the community. Usually I speak to probabilists, so this is, for me, it's very interesting to speak to mainly, I saw among others, mathematical physicists and physicists, maybe, I don't know. So this was, I am using just slides for a general talk, so forgive me if all this is trivial for you, but even for myself, I sometimes need to really think about what I want from life and what I want from an Euclidean quantum field theory. And actually, I always don't know what I want, because people start with these metaphysical formulas, and which, when you look at as a mathematician, when I was a physicist, was trivial, and now it's incomprehensible somehow, this formula. So I shift from one side of the spectrum to the other. But I found on the archive some preprints from physics, like this SNOMAS project in the US. And actually one of these preprints, you can find the SNOMAS, and it's about quantum field theory. And there is a claim made by physicists that we don't know what is a quantum field theory. So this reassures me somehow that we are not alone in this quest of a rigorous definition of what we are looking for. Of course, you can say Whiteman axiom, but certainly it's the minimum requirement. So to have more clear understanding what is the structure we want without using an approximation, for me, it's a challenge and very interesting as a mathematician. So with this introduction, so this is the kind of object I'm interested in. I cut short. Essentially, they have two kind of problem to give a meaning to this formula. You have a problem because you want to integrate over the full space, because you want to create an invariance. And you have a problem on the small scale, essentially because you want reflection positivity. Okay, here we are in the Euclidean, and from the Euclidean to go to the real world, to the real Minkowski setting, we need some technology, and this technology, maybe it's Osterwalder-Schrader or other things, but certainly anything will contain this kind of problem as far as the kind of, in the constructive point of view. Okay, and this slide summarize a bit what I consider the main progress at the beginning, or which consolidated this beautiful discovery that you can construct a certain model in low dimension, like 1, 2, 3 Euclidean dimensions, interacting quantum field theory, and certainly the work of Gliman Jaffe, but also all the other person I mentioned. I really spend all my initial period really studying all this work, and everything was very interesting to me and very challenging. And yeah, so for a long time I stayed away from this topic because I was considering too difficult, and actually still too difficult for me. So I tried to find another way to understand the same thing. So this is the topic of my talk, okay? And yeah, so you want to construct these quantum field theories and the Euclidean setting. The simplest is the Gaussian, and you can do Gaussian free field. You can do Gaussian free field with some fractional Laplacian. This is still reflection positive, and but certainly all the example of Gaussian we know are distribution, especially in dimension bigger than 1, 2, 3. Yeah, and then so you have problems. Okay, so essentially the simplest theory we know to construct the Gaussian free field is not a regular function, it's only a distribution. It's a probability measure on the space of distribution of regularity, which we can characterize, which is given essentially in 3 dimensions is -1/2, in 2 dimensions is logarithmic, or maybe all you are familiar with that by now. So this is the reflection of the problem on the small scale at the level of the Gaussian. And then you want to construct the Gaussian field because you would like to have interacting particle when you go back to Minkowski space. And then essentially the only sure way we know to do it is to perturb the measure. You go on the lattice, you go on a finite volume. So you have an infrared and ultraviolet cutoff, and then you can put an interaction. You have like an unbounded spin system, and you try to put the parameter in such a way that you have a well-defined infinite volume limit and small scale limit, which is non-trivial. And then you can start to ask a question about uniqueness, non-uniqueness, correlation, description of this measure. And some of these questions are somehow never. So I think they're never asked, like how we can describe the infinite volume measure without the cutoff. In my mind, this is still an open problem, and any description you give guarantee you uniqueness or not. And in my mind, these are very open question. Okay, I don't know any reasonable answer to this question, but you can challenge me, and I would glad to learn about it because I don't know how to describe the infinite volume. So for us, for example, when I will speak about 543, it's a very precise construction. That is, I take this model on the lattice with a 4th order potential in 3 dimensions, and I try to take a limit. And if I get a limit which is non-Gaussian, I call it 543. Okay, this is very clear recipe. I don't think it's a definition, but at least it's something we all agree and understand. And then, so this is what is a quantum field theory. Then what is stochastic quantization? Actually, the talk is, I don't know what is stochastic quantization. I have some idea, and my idea change with time and become more interesting. Actually, at the beginning, of course, you take this word from the word of Parisian Wu, which somehow used this idea of introducing an additional dynamics and looking at, so you introduce you look at the Lagrange equation, which is a gradient flow for a certain functional with additional noise. You take this noise to be space-time white noise. Now this time is a fictitious time, simulation time, call it whatever you want. And the X variable is the Euclidean space. And then you want to study the equilibrium of these dynamics, and under reasonable condition, this equilibrium should be given by the quantum field theory you would like to represent. Okay, so this is a way, they introduce it as a way to construct the functional integral in situation where the functional integral was problematic, like in gauge theories, but you can think as a general way to construct quantum field theories. Okay, that's why stochastic quantization. Edson also introduce other kind of stochastic quantization, but I would like to speak about this one for the moment. And I think I will try to show you or to motivate the fact that this is one way to understand what is stochastic quantization. There are other ways which have nothing to do with the Markov process nor with the Lagrange equation, but all the ways somehow they are subsumed in this interpretation. That is, I think this is the useful way I think about stochastic quantization. It's a way to transform a Gaussian field into a non-Gaussian field with a prescribed property. In this particular case, all you want, that is Euclidean invariance and reflection positivity. Okay, and actually, there are not so many ways we know how to do it. I will list the way I know how to do it. There could be other ways, but certainly the ways I will show you, this way it's interesting because it's amenable to a lot of analysis. Okay, so there are abstract ways to do it. So you can always transport on a measure on another measure under certain condition, but then it's difficult to control the map. But certainly this interpretation makes links which are novel and start to be explored in the last year, also thanks to the work of Roland and Bodino and people at MIT, people around the group of Eldon, that they were trying to understand functional inequalities via transport through the Gaussian. Okay, so this transport theme is interesting in its own way. For us, I don't care about transport interpretation. I want to have an easy transport interpretation, which I can analyze and use to prove property of the field using the properties of the Gaussian. Okay, that's somehow the goal, and that's what I would try to convince you it's the main advantage of stochastic quantization in some ways, okay, or the main interest of stochastic quantization. And this is the history of stochastic quantization, which is partial and personal. And certainly I would like to, again, okay, there are this contribution of Nelson, but in my mind, Nelson's approach to stochastic quantization is a bit different, okay? So let me put aside, I mean, Nelson is a very important reference point, but here it's a mini history of just this way of doing stochastic quantization, which started, as far as I know, with Parisian Wu. Of course, people were doing Monte Carlo before, but somehow they claimed that this was also useful theoretically, not only in practice to sample these things, okay? And then right away, John Alazine and Mitter understood how to do it rigorously on a bounded domain and only in two dimensions. And then there are this very interesting book of Damgard and Uffel, which resumed a collection of paper. And essentially, the last year, my work has to be just to take one paper and make it rigorous. You take the second paper, you make it rigorous, and you go on until you can do it anymore. And so far, it worked and actually give very interesting things. But essentially, it's the job. Now, lately, I discovered this part because I was asking myself, okay, how you control correlations in stochastic quantization in an intrinsic way. And Parisi, of course, wrote a paper. Paris wrote a paper on everything, so you just have to find out the paper. But somehow the best approach I found in this paper of Funaki, after thinking of myself, but then when I understood what one has to do, of course, people already did it for smooth reversible dynamics, but essentially, in this paper, in an appendix, Funaki used coupling to control correlations for smooth reversible dynamics. And once you understand this is not has not been done, we are doing it, but you can do it also for certain stochastic quantization. So just to mention this paper, which is meaningful to me. And then this is going in the direction of characterization. There are this work of Kirillov, which are also very interesting. They are related to the fact of integration or topics around integration by parts formula. No, you want to characterize a measure by saying this measure has a given integration by parts formula. For the Gaussian works, okay, the Gaussian is the only measure which has the integration by parts formula you expect from the Gaussian. And for non-Gaussian measure, it's an industry and it's sometimes difficult. And Kirillov did interesting example in infinite dimension. Okay, I actually is the only one I know which gave interesting example in infinite dimension. There is a book of Bogachev for finite dimension, and then it's difficult because you can do complicate things in finite dimension, but in infinite dimension there are this work of Kirillov. And then this work, Russian school were very active in that period, and actually they studied the stochastic quantization, and they were using method of constructive quantum field theory, like cluster expansion, to study stochastic quantization. And okay, then let me, Albeverio also studied integration by pair formula. So I'm citing some paper I find very interesting in this idea. And then the modern history somehow, from the SPD point of view, start with Prato de Bush, which understood how to construct essentially the dynamics for 542. And then the breakthrough of Feiner with regularity structure and the analysis of the most scaled structure of 543. And then globalization of this result by Murray and Weber. From my point of view, for me, has been very useful this paper of Albeverio, because technically it's not so easy to globalize the result and to really do all the program of stochastic quantization, which in my mind it's really to use the equation to study the measure. So it's illegal to use any information about the measure before you know it. So otherwise, it's a trick. Okay, you're not doing stochastic quantization. You're studying the dynamics. A Markovian dynamics, which you can do, it's very interesting, but it's not stochastic quantization, okay? Stochastic quantization is you start from the equation and you construct the measure. If you have to use the information about the measure to construct to say something, then it's something else, you're doing something else. And then we somehow, in our work with the Hoffmanova, we just put all the ingredients together and verify some axiom in 543. We don't have rotation invariance because uniqueness, okay, we can do any lambda, so it's a non-perturbative result, but we don't have reflection invariance because we could be in, we don't have uniqueness. And then there is this impressive work of Chandra, Chevirev, Feirer, and Chen, two very long papers, very difficult, but very stimulating, which they started stochastic quantization for young meats by studying the local problem on a bounded domain. Okay, again, globalization is still on time. Okay, this is the so far. Okay, what we know so far. Okay, so Parisi-Wu. Yeah, so how you do for 543, I just want to give you some word. Well, the idea is that you start from the lattice, you do the stochastic quantization in the lattice on a finite volume. This is exercise in stochastic analysis to do. There is an invariant. I don't even need unique because I'm not claiming anything about uniqueness. Let's say I just give me stationary solution of this equation, which has 543 lattice, 543 as invariant measure. This is allowed to use because in some sense, lattice 543 is a trivial measure. You don't have to do anything to know that it exists. And then the point is that now you want to study just the map, okay? You look, this is a map which goes from the white noise to this stationary process. And then somehow you want to study this map so that you can take the limit epsilon and in epsilon and n. And the result in this paper with the Hoffmanova was that, it's more or less what I paraphrase here, that you can take the limit, there exists a limiting object, which is a stationary solution of some equation, which you have to renormalize, so you have to understand properly. But from the point of view of stochastic quantization, at that point, the interesting part is that this implies the convergence of the regularized measure to some measure. And then I would like to say something about this measure, and what we know about it is satisfying integration by parts formula. By this formula, I feel the right to call it 543, okay, because I see the cube. And this renormalized cube, what I find very interesting, that in order to do so, you have to define the cube, and you discover that the cube, this was already known that the cube is not a random variable. So it's a distribution for the measure nu. So you cannot, it's not a random variable, okay? It has to be understood in duality with nice cylinder function. Okay, and the dynamics allow to prove this. Okay, so somehow the dynamics give you a very nice decomposition of the interacting field, which allow to you to prove that the cube of the interacting field is actually the cube of the free field plus nice correction terms. Okay, and this gives you I mean, you have a coupling which you can use. I mean, and Roland know this thing because you can do similar thing in renormalization once you know a bit what you want from life. Yeah, so what is the feature if I want, so this, I will not speak about technical result, okay? We just want to give you a map in such a way that then you can read the work because you can skim over all the technical estimate and you can arrive at page X where something is going to happen, okay? And the idea is that, okay? The idea is that once you've wrote your solution as a map from a Gaussian, you know very well the Gaussian, you know very well the map, which is a PDE. Then for the map, you use PDE estimates. For the Gaussian, you use probabilistic estimates. And you finish your work by putting all these two things together. This idea comes from rough path theory, then Martin used it, and we used also with co-authors, and this is very fruitful. And somehow, yeah, somehow you use the message, use probability when you need it, but analysis is usually most flexible when you don't have to deal with adaptedness, with things like this. And then what it gives you, a coupling, I told you already, between the interacting field and the free field, which you understand very well, okay? And you see this transport point of view is very powerful because you can transport the Gaussian free field into a measure which is not absolutely continuous with respect to the Gaussian free field. While if you want to study the interacting measure as a perturbation of the Gaussian free field, you have to do a lot of work because it's not absolutely continuous, okay? So this is trivial thing I explain very, even to my students. So Brownian motion, 2 times the Brownian motion is not absolutely continuous with respect to Brownian motion, but the map is trivial. So if you insist to look at the absolutely continuous perturbation, you are doing the wrong thing, okay? In this case, it's more useful to look at it as a map because it's kind of way to look at this problem. I mean, you don't, so this is what we are doing, okay? I insist that stochastic quantization is just a map which transforms Brownian motion or Gaussian free field into interacting object. Yeah, and then, okay, this is the way you do the estimate. If you ask question, I can do into the detail, but essentially, you can do a lot of things with the stochastic quantization, and it took some time to understand, for example, how to do the optimal estimate on the tail of the distribution. This you need for the Osterwalder-Schrader to go back and to have analyticity. Okay, so this is key to analysis, to have good tail estimate of your measure. And at the beginning, it was not clear how to obtain with stochastic quantization. It required somehow Monod, Weber had them with alpha less than 1, and then we copied their idea. And somehow the good idea come from Eirer and Steele, which is a very small paper, but they get the right idea to do it. And now it's clear how to do it. And it should have been done in this way all along, actually. But yeah, okay, just to mention in this way. Okay, and then now we have this estimate with optimal exponents. Essentially, alpha can be 4 because with the right topology. Okay, so because the tail you expect for 5-4, you expect 4th order tail. So you should be able to integrate the 4th power. So and this is possible if C is small and the norm is sufficiently weak. Okay, so was a small introduction. Please ask question if you feel to. I don't want to insist too much right now because for me, maybe I have a lot of slides and I want to make this point maybe to see where I'm aiming for. And you see, and this is, so try to merge, you try to merge two fields, constructive quantum field theory and stochastic analysis. And I'm teaching stochastic analysis, and I don't have a definition of stochastic analysis, okay? I cannot tell the students, this is stochastic analysis. I know how to, if you give me a paper, I know if this paper used stochastic analysis or not. And essentially, more or less, you can say stochastic analysis is what Ito did and what Machiavelli did, okay? And if you use Ito calculus or Machiavelli calculus, then you're doing stochastic analysis. So what is the difference between stochastic analysis and usual analysis? Why you call it analysis? First of all, well, because I try to build an analogy. So Newton, why introduce analysis? Well, he had a global object, which are a planet orbit, and with a global description, which is an ellipsis, sorry, and then you introduce a parameter in this description, and then you, with this global, you can decompose this global description locally, because when you have a parameter, you can look locally what's going on. And then you have a local description, which is then give you this notion of derivative, because you approximate with polynomials. And then you can write a differential equation, which is your link between this local description and the global object, okay? And the discovery of Newton was that he was able to go back and forth between the global and the local description. So they were equivalent. And Ito calculus has the same history. I read a beautiful book of Struck about Ito approach to diffusion. And he recounts the history of why Ito invented his calculus, and he wanted to understand Markov diffusion, the theory of Markov diffusion, which was understood at that time via analytic tools like PD equation and generators and all this stuff. But he wanted to understand, so this is our global object, is a Markov diffusion, it's described by Markov-Mogorov equations, and you want to solve these equations. And then you introduce, here you have a natural parameter, for example, already, you have the time, so you can do a small time change, and you realize that the kernel looks like a Gaussian for small times, when you change the time, when the time is small. And then the Gaussian, in this case, is infinitely divisible, so it's actually the Brunner motion. And then the idea, so this is the parallel, okay? The local description is this Gaussian approximation, which has a drift and has a covariance matrix. And then the building block is the Brownian motion, which is like a polynomial, which allow you to approximate locally your diffusion. And then the global to global, local to global link is the SD. If you solve the SD, you go to the Markov diffusion, and the SD contain only the local information, okay? The drift and the covariance matrix. Actually, here I wrote it wrong. It's more like the square root of the diffusion matrix. Sorry. Okay, and then if you think in this way, rough path is another way to do stochastic analysis. If you want, regulative structure is another kind of analysis where you don't use polynomial, but you use arbitrary set of objects. SLE is still an analysis, okay, because your local object is the Brownian motion, which generate a small diffeomorphism, a small conformal map, and then you construct global conformal map with only using the driver. Okay, so Loessner chain is an analysis, different kind. Okay, so I like to think like this, and maybe it's not completely precise, but this is heuristic tool to do something. It's not a theorem. And then stochastic quantization is a stochastic analysis. Well, let's try to fill the blackboard. The object is the Euclidean quantum field theory. The global description is this mythical path integral. And then, of course, here now we have to have some fantasy and find a parameter with which to do analysis. So Paris and Wu, they choose this additional time parameter, so they added a parameter. So somehow this problem looks different because you don't have a natural parameter in the problem right away. So you have to introduce in one way or another an additional parameter. Once you have introduced the parameter, somehow this guides you to how to do the analysis. So if you introduce the additional fictitious time, then you have this diffusion. Locally, the diffusion looks like a dynamical Gaussian free field. And then you the equation is the stochastic quantization equation. Okay, again, this is a heuristic table. Okay, I'm not claiming that you have a factor between categories, even if somebody maybe can do it. Okay, but just to have this heuristic picture. And maybe there is a factor, but I don't know. Okay, I never really thought seriously about formalizing this. At this level, I think it's useless. I mean, we need to understand and then we can formalize. And then just to show you that there are many stochastic quantizations, let's show some of them. The parabolic, I told you, one additional real parameter, you do parabolic equation, you are done. You can do with a wave equation, again, one additional time parameter, but then it's called canonical because you have a canonical, this is equivalent, this is like, this quantize the Lagrangian path integral and this quantize the canonical path integral, okay? This is the difference between the two. But again, it was discovered by the physicists. Just from the mathematical point of view, it's very interesting. It's a wave equation, so completely different from the other. It's very difficult to study. We made a bit of progress with collaboration with Koch and O, but like the other day, John Brinkman sent me a preprint where they wrote an impressive solution in 3 dimensions. Okay, so now they are able to do it for 3-dimensional 543. It's 200 pages paper. I'm just only worried to open it, so maybe I will do it in the next few days. But it's very impressive work, but this showed that somehow this does not bring anything to stochastic quantization because this equation is difficult to study, so it's not very interesting for us, okay? You cannot use it as a building tool. But certainly it's very challenging, it's very interesting to know, because for example, the wave equation has no regularization coming from the Laplacian, but you expect to have the same renormalization constant. And before the last week, I was not even sure this was true, okay? Of course, formally, you can argue that this is true. In perturbation theory, you can compute Feynman diagram, this is true. And then recently, they using this, this paper that I mentioned, they do it. The invariant measure has to be 543, so the renormalization constant has to be the same. The diverging part of the renormalization constant, okay? But this equation has really different regularities somehow. You cannot, it's very difficult problem, very interesting. But okay, stochastic quantization is a bit useless because I cannot use it right away. Actually, they use this in a way which I still have to understand. So they use the parabolic to understand the canonical. Okay, so that's very interesting. And that's similar to what you have to do in Yang-Mills theory, for example, to do stochastic quantization of Yang-Mills, which is parabolic stochastic quantization, but then you have to use the Yang-Mills heat flow to understand the parabolic stochastic quantization. Okay, so you have interaction between different PDEs in order to understand them. Very interesting. Again, okay, time is not necessary. Okay, you can do it without time. You can do it without Markov process. So Markov process theory should not be an intrinsic property of stochastic quantization. In particular, in this paper with Albeverio and De Vecchi, we proved that you can do with this kind of elliptic equation in D+2 dimension. Okay, you have to do a 2-dimensional parameter. You don't use the derivative of the parameter, you use the Laplacian of the parameter. And these have the same singularities of the measure and of the parabolic. And it's as difficult to study. The parabolic is not easy to study, okay? So more or less what I can do for the parabolic, I can do for this. And even if it's completely not true. So if you ask me, I will comment about it. Just to say that it should not be a Markov process, they are not written anywhere. And then again, okay, with Barashkov, we introduce an equation. You don't see an equation. So at the beginning, we were not caring about the equation, we were caring more about renormalization group. Renormalization group give you Hamilton-Jacobi-Bellman equation, and this is difficult to study, so we prefer to study the control problem, and the control problem, you see the cursivity better, and indeed we proved that you can construct 543 on the box with this method. and with idea coming from renormalization group, okay? But you have to realize that this is still an equation because the optimal control in a control problem is essentially usually a feedback control, so it solves an equation, okay? We don't write down because we didn't need it, but this is still there, and actually this is useful in infinite volume where you cannot write the action anymore because it's infinite, but the question exists also in the infinite volume, okay? So this is still an equation. This is why I claim that all these methods give you a way to transform Gaussian free field into interacting field. This is just a different way to find an equation. But you see, the elliptic equation, any elliptic equation, comes from a variational problem. This is not true for the parabolic, okay? So for the elliptic equation, you have this is the first order condition of a variational problem. In particular, you have a second order condition, which I don't know what does it mean, but it's there, okay? The second order condition means essentially that you could imagine, okay, the second order derivative is positive, okay, of the functional. In the parabolic, I don't see the same structure, so this is a bit different. In this approach, you see the same structure because you have a variational problem. So you have a second order condition which tells you that, yeah, and in gauge theories, you also need to have a second order condition. So this is interesting in this respect, okay? So now, let's just I mentioned there, I'm not sure what does it mean. So, okay, let me, how much time do I have? 50 minutes, so overall, I mean, yeah, I don't know, 5 minutes.
I think 50 minutes or an hour, it doesn't matter how much you like.
No, okay, let's say, no, I don't want to kill everybody, so let's say I try to do in 10 minutes this example. I want to give you the example, okay? An example which I didn't mention, because also, I mean, the title is a question because in my mind it's not clear what's going on yet. That's why also we write a paper with different methods because I don't know what is the best direction to use. More or less, I'm realizing that what I can do with one method, more or less I can do with the other method, and there are not so many advantages. No, it's not clear that one method is better than the other. The only method I don't know how to use effectively is this one, because I told you it's difficult. You need really expert in dispersive equation to even write down the definition of the space in which you solve this equation. But for the other method, they're all easy parabolic or elliptic equation. The theory from the SPD point of view, from the PD point of view, is more or less trivial. The point is to put together various ingredients, the renormalization and the control of the large scale. But this you already know, okay? If you know the work of Bridges and Bauer, Schmidt, and Slade, you know that to do effectively renormalization group, you need to have a good control of the larger scale with the good nodes, and then you can expand in the small scale, and it's the same with the work of Baraban, okay? You need an effective tool to separate the large field and the small field. So this we do with PD tools, essentially. Once you have an equation. So you need an equation, and I want to show you that the variational method gives you an equation, and is not related, and you can use the variational method without using renormalization group. So the fact that you want to use renormalization group, you can put on top of any of this approach. It's not separate, okay? It's complementary, okay? So the small scale can be studied with renormalization group, can be studied with the paracontrol distribution, can be studied with rough path, can be studied with the regularity structure, whatever you like. The larger scale, you have to find some coercivity, otherwise you're dead. And to put them together, it's somehow interesting aspects in this job right now. And then let's use the variational method to do 542 in infinite volume. Is easy, so we don't need renormalization group here. We can do with just some estimates. But let's think about it. Okay, so how we do? Well, we start with this formula, which I find very nice. I teach to my master's student because it essentially contains anything you want to know about Brownian motion. It tells you that whenever you have a functional or of a Brownian motion, it could be infinite dimensional. I do in Rn, but it's uniform in N. It's a formula, so it's uniform in N. If you, this quantity, so this expectation can be computed as a control problem. You just, instead of having Brownian motion, you control the Brownian motion by adding a drift. You pay a price for the drift, and then you take the supremum over all the adapted control. And this quantity compute the right-hand side. Okay, this is a variational formula. You recognize a free energy. Is not exceptional that you have a variational formula. The exceptional thing is that for the Brownian motion, you can write a very easy formula. There is no entropy. The entropy is quadratic. And that's allow you to do a lot of computation very directly. And in a matter which become complicated very fast, it's useful to have an easy formula to start with. This comes from Bouet-Dupuy. And this you can use to what you do. Well, I want to compute I want to understand the interacting measure. This formula essentially allows me to compute its Laplace transform or the free energy, whatever. You understand very well that if I have the free energy, I have everything. So this is the free energy of the interacting theory. And I write as a variational formula, and I need an additional parameter. This parameter is not doing anything. It just goes from 0 to 1. It gives me an infinite divisible decomposition of the Gaussian free field, but it's not linked to a scale decomposition, okay? This I can do because I'm two-dimensional and it's not very singular. So for any time, this field is still distributional, it's a Brownian motion which at any time is a Gaussian free field with a given covariance. Very easy, okay? It's a Brownian motion with the covariance of the Gaussian free field. So there is no decomposition in scale. If you want, you can put the decomposition in scale, but in two dimensions you don't need. But you have to keep in mind that now you have this Brownian motion is irregular. You have a control. You write down your things, and you get a formula for the infinite volume for the free energy of the 542 theory as a control problem. You have the energy, which is essentially the kinetic part, and you have the potential part, just written with this additional variable. But formally, you recognize very well variational problem. Okay, so somehow, you see, you put a quantum problem in a classical problem, but with an additional parameter. If you want, okay, I can put it in this one. This is the quantum partition function, Euclidean partition function. This looks like the classical partition action, but with this additional parameter. And sorry, there is an additional ingredient, okay? So the unknown is Z, but now, there is an average. Of course, the quantum, if you want the quantum Euclidean quantum aspect, is still given by an expectation because you have the Gaussian free field, okay? So the kinetic energy is only for your drift, what you want to put, but the potential term, you pay what you put, but also a Gaussian free field, which you cannot control. And then you write, okay, this is cosmetic. The point is that, okay, you can control this. It's not very interesting right now. I want to make the point that, that it's a control problem. So it has a minimizer which satisfies a Euler Lagrange equation, okay? And you can write down the Euler Lagrange equation. Let me see if I wrote down. Yeah, so let me say you something. Like you can write the Euler Lagrange equation and it looks like this. And once you have the Euler Lagrange equation, it's obvious how to take the infinite volume limit because it's an equation and you know how to handle equations. Okay, you do a priori estimates and you take the limits. And so from this point of view, but you need to go to the equation because the variational problem does not have an infinite volume limit. Okay, of course it's infinite. So you go to the equation, you go to the critical point of the variational functional, and then you can take the limit. You don't have uniqueness, but you have a converging subsequence. This is enough to have some result at the end. The point is that any minimizer somehow gives you the interacting field. Okay, this is the idea you want to have. That is the minimizer of the variational problem solve an Euler Lagrange equation, And this Euler Lagrange equation, which is written in this way here, it's a strange way, but it's an equation. You see, K is a test field, okay? So you test your variational problem, then you write the first order condition. You see this is linear in K. And then this should hold for any K, and it's a weak form for an equation, which also is a stochastic equation. You need an expectation. But the minimizer, for example, in some case, you can show that it's unique, then this will be the interacting field, okay? You can show that in order to compute the average over the quantum field, you just compute the average over the minimizer. And this is a strange stochastic elliptic problem because, okay, it looks elliptic, but somehow it's not, somehow you need to, the solution has to be adapted to the noise. So you keep some information from the stochastic structure. But it's really an equation, okay? If you handle it a bit, so if you want to see an equation, it looks like this, okay? So you have this additional parameter which go from 0 to 1, and the solution z. So you're looking for a function z which is dependent on space and time. The derivative in time to z satisfies an elliptic equation. This elliptic equation has nonlinear right-hand side. But the right-hand side depends on the solution at time 1 and on the conditional expectation of the solution, okay? So it's not a PDE, it's somehow a problem where you have a stochastic process and the right-hand side depends on the law of this process because you have to compute the conditional expectation. And if you, you solve as you solve a PDE, you do a fixed point and you find a solution. There is no problem, just simulate, okay? But again, this is another equation which is not mentioned in the list above. Okay, this is given by the variational problem. And in some problem in which we can show uniqueness, we can prove even that it has a unique solution and that the solution is represent the coupling between the Gaussian free field and the quantum interacting field. Okay. So again, okay, complete somehow this kind of stochastic quantization. For 542, we don't have uniqueness because the microscopic potential is not convex, okay? Roland knows very well the problem. He even wrote papers recently about Sobolev. So I think here you really, I now maybe understand how to use the renormalization group to get this convexity, at least when lambda is small. Also thanks to the ideas of Roland, but in this approach, I don't know how to prove it because now you have to subtract an infinite constant and phi4 is not convex anymore. Okay, of course, and people know it. But if you have convexity for things which are convex, we can do a lot of things. So for example, sorry, I didn't mention, but this thing I did with Barashkov, and you find the paper on the archive, is on the thesis of Barashkov, which was a student in Bonn, and now it's in Helsinki with Kupiainen. And you can do for the exponential interaction, which is convex also after renormalization, and then everything works nicely, of course, okay? Because this exponential interaction only get you higher mass, and so you are in a very happy situation. But still, it's tricky, okay? It make appear and you can write even, yeah, this is maybe nice to know that in this case where we have a lot of control, we can do gamma convergence and we have a variational problem in the limit. And the variational problem is of course not the energy of the ground state, but somehow you do a variational problem where you perturb with respect to the ground state, okay? So you see that, the variational problem has this form, okay? So this is the variational problem for the infinite volume limit. You have the Gaussian free field, you have the interacting field, which is the solution of the Euler equation, and you have the test field for the variational problem, okay? See, so this is a perturbation around the ground state of the exponential model. You have a variational problem in this way, okay? But this is a complete characterization of the exponential model in the infinite volume and without cutoff, for example. Okay, this describe it's an explicit description of the Laplace transform. You see here, okay, it's an explicit description of the Laplace transform of the exponential model. So in this way, you really read it here, and you can do large deviation if you want, for example. Okay, so, and then we have another, I think we understand a bit how to do also with fermions, okay? We have a paper in finite dimension, and we are working in infinite dimension is tricky. So how to discuss renormalization with fermion, we don't know, but in this paper we proved at least that the infinite volume limit, we can do stochastic quantization. For some models, of course, for regularized model with cutoff. Okay, and these are some papers. And again, the last part of the talk was based in this paper with Balashkov. And if you want to see a complete construction, for example, in this paper, you use the control approach to give a complete construction of Saint Gordon, which you can do in some region of the parameter space. Okay, because then in the stochastic control approach, you have a renormalization group, so you can see see the convexity of the potential at given scale. Okay, let me stop here. I think I even went off time. Sorry for that.
Well, thank you very much for this very inspiring, interesting talk. Are there any questions?
Hello, I have a question, please. Thank you very much for the very interesting talk. I just have a question concerning the application of stochastic quantization for in the case of an Euclidean space, but some Euclidean symmetries are not with no Euclidean symmetries. Like, for example, for a half space, for example.
Yeah.
Is it only? I want to understand how actually the Euclidean symmetries enter in the stochastic quantization.
Yeah, so now for us it's a problem. Okay, so the point. So yeah, maybe I did. Yeah, so I was a bit fast at the beginning because I was counting on you to know everything about it, but somehow. No, I'm joking. I mean, the point is that, so there is something I didn't talk about is, I mean, real quantum field theory lives in Minkowski space. So we have no Minkowski metric, we have the Euclidean metric, okay? And the recipe to go back require that you construct. So what you have to show it exists is a measure on the space of distribution, which is stationary with respect to rotation and translation over all the space, okay? So this translates on the other side on a theory which is fully Minkowski invariant, essentially. So if you don't have all the symmetry, you cannot go back. So as a probabilist, maybe you don't care, but then it spoils the application to real quantum field theory. And actually the difficulty, the large scale problem, if you just want to work on a torus, you can do as a probabilist, but then you cannot use this to construct a real quantum field theory. Okay, so if you want to work in enough space, as far as the technology, okay, you have to decide what you do at the boundary. Yes. You can do periodic boundary conditions in this direction. Okay, for example, reflected. I don't know. You reflect. I don't know. You have to decide what you do at the boundary. You can do the Dirichlet, you can do whatever, and then it's a PD with some boundary condition. Still interesting problem, maybe difficult because near the boundary maybe renormalization is different. Technically, it does not cause big problem. Okay. In the general approach, if you have so. There is a small technical problem when you discuss renormalization constants, because there will not be constants anymore. So somehow you have to subtract infinite quantities in these things. And if you are not in an homogeneous setting, you might have that you have to subtract things which depend on the point. But conceptually, it should work. Okay, so in my mind, okay, this is very vague because I don't know exactly the condition, but I could imagine that you can make sense of 5 or 3 on a half space. There should not be problem. I mean, I don't see any problem.
Yeah, thank you so much for the clear answer. I just want to know if it is also related to identifying the Brownian motion on the half space. Because we have, like, if we see just the possible Brownian motions on the half line, we have many that were identified by Feller with William Feller with a very nice.
Yeah, but with this, okay, this from the point of view of the PD would depend if it's a PD. So you have to specify the boundary condition. So
yes.
This will give you the Laplacian. So in this PD, there will be a Laplacian with some boundary condition. And this Laplacian with some boundary condition will be the generator of your Brownian motion. So the boundary condition for the operator to be self-adjoint will correspond to what happens to the Brownian motion. But you should not confound the Brownian motion I'm talking about with somehow, I mean, the Brownian motion you're talking about is the process generated by this operator. Okay. This operator, if you do in the half space, you will have to say what happens at the boundary when you solve the PD, because then the PD you have to say something how you handle it on the boundary, and this will force you to somehow this corresponds to some Brownian motion with some boundary condition. So if it's reflected, it will be Neumann. If it's a solved, it's Dirichlet, and so on.
But I don't understand what is the other Brownian motion. So there are 2 Brownian motion. One which is associated to the Laplacian operator, and what is the other?
Yeah, that's the idea. So that's the point, okay? The other, it's an external ingredient, okay? That's the idea of Parisi-Boux. So since the subtle thing is the thing you never saw, and actually the first time I saw this formula, I didn't saw it, and I never saw it until we discovered that it's easier to solve this equation than actually to construct 5 or 3. So, I mean, in my mind, constructing the dynamics, it's easier than to construct the measure. And then you realize, okay, why it's so easy? It's because actually construct the dynamics, you can start from an object you know very well. Again, so you see, this is the Brownian motion. This is a white noise, but of course, it's, I mean, if you fix the point in space, you look in time, it's the derivative of a Brownian motion, let's say about it. Okay, so is this the Brownian motion I'm talking about, okay? So so if you think how you solve this PDE, you are given so how you have to do to solve it, well, you sample this Gaussian process, and then you construct the solution with this Gaussian process as a forcing term. Okay, so let me go back to a more synthetic slide. Okay, so you are interested in a stochastic process, and so this was the Ito idea. Okay, so this is Ito contribution to stochastic analysis. People were studying diffusion process. Okay, Feller was studying Feller process, but looking at the generator. Okay. You don't see the path of this process. But then it arrived and, okay, I want to look at the path of the process and I want to write an equation for this path. And then he wrote an SD. And in this SD, you have your process, which were there from the beginning, is the object of Markov process theory, but you have a new object, which is the noise, which produced the process in Ito point of view. So Ito point of view is that I want to produce a complicated object, which is a Markov diffusion, from an easy object, which is Brownian motion or white noise.
Yes.
Okay, so this is, and I mean, in Struck's book, it's written that Ito were going in the 40s in the US to make seminar, and nobody got the point. Okay, and only McKean and only Doob understood what's going on and then followed up. Okay, so it's a key idea which is very simple and which you miss because now you teach to the student they think it's trivial, the SD is trivial, but it's the idea which is revolutionary and which introduced stochastic analysis. Before, people were not doing stochastic analysis, were doing theory of Markov process or functional analysis with some very difficult generator. It's not, yeah, Levy was doing already something like stochastic analysis. And Döbling was doing stochastic analysis, but Döbling just decided to put everything on a letter and forget it until 200. Okay, so the point is that you don't understand because it's a deep idea. The idea is that I want to study a process, I introduce an easier process, and I write my process as a function, as an easy function of my easy process. So I decompose the problem into parts now.
Okay, thank you so much.
Okay,
Thank you.
yeah, sure. And yeah, I didn't understood myself at the beginning. I was thinking that until recently, I was thinking that all the point was somehow I never understood before the interest of stochastic quantization because the interest is not apparent. So if you look at the theory of stochastic quantization, so the interest of stochastic quantization, in my mind, starts here. Okay, before this paper, all the previous paper used knowledge of 543 to construct what they need. Okay, this was the first paper to me that somehow cut the Gordian knot and freed us from knowledge of the measure. And there is a very trivial trick, very fundamental trick, which Albeverio knew because essentially he's thinking about these things since he was a kid. And for him it was trivial, but somehow is an easy trick. Because you see, if you do a parabolic equation, you never get rid of the initial condition, okay? So this always bites you back, whatever you do. And in this paper, there is a trick which gets rid of the initial condition. You can use coming down of infinity. So if you want, somehow we start to understand how really to do things in these two papers. Even higher with I don't remember the co-author, it's not Mattingly either, and they write a paper by showing that on the torus, the dynamics was really the invariant, I mean, as invariant measure 543, but they were using the knowledge of the measure to construct this knowledge. Okay, they were using previous result about the measure. So the papers who cut this Gordian knot was somehow coming down from infinity at this level was not good enough because coming down from infinity is already good because it tells you that you have estimate on the equation irrespective of the initial condition. So it's a way to estimate nonlinear parabolic equation without knowing anything about the initial condition. And then in this paper of Albeverio Kuzoka, there is another trick. And in this paper, we use this other trick because it was technically easier. But I think you can use also the kind of trick they used here. Now I understand better how to do it. At that time, I didn't. So I think real stochastic quantization really started here. All the rest was preliminary work to get. Now I think something interesting was happening also here. Okay, but all the other work use. Yes, in some way these use cluster expansion, which somehow is contrary of the spirit to stochastic quantization in my mind. Okay, sorry for this divagation. I mean, I'm not claiming they are not legit work, okay, but somehow they are more in the spirit of Markov process theory. Okay, you have a dynamics and you want to study the invariant measures to this dynamics. So you have the measure, or you want, and then you have to somehow you use properties of the measure, especially in these very singular situations in many of these papers. I think, yeah, sorry. Yeah, okay, stop or I still continue. Comments.
So what you say, maybe if I can ask a little bit provocatively, I was reading this Parisi-Vu paper the other day just for entertainment, and they conclude that it's not very useful practically. But I think would you agree that your point is that so they argue it's useful as a theoretical tool to know that you can avoid the usual tricks that are usually used to for gauge fixing, etc. But practically you wouldn't use it. But your point of view is that practically it's useful because you don't talk about. I mean, your interest is in the practical construction and not these issues that they were concerned with. Is that correct?
But this was. I mean, I think this. Yeah. So the claim is nowadays we really. I think we wrote really a paper because we were not sure we could. You see, you could say you can do it, but and it's written this part, it's written this paper in this paper, but the assumptions are different. If you want, so we really wrote a paper as a homework. So let's say if we can do it, and I find the paper relatively okay. I mean, and we understand. I think at this point, this talk is also a message to say, to me it's a legit constructive tool. It's independent of any other constructive tool. I more or less have some idea even how to prove decay of correlation without cluster expansion. My students always, no, because I go around and say, no, I don't want to use cluster expansion. I want to do it with the equation. If somehow in my group, the things is, if you don't use the equation, but use other information, I don't want to see it, okay? You go in another group. That's not my business. For example, yeah, okay, and it's a joke, but okay, it's because if you want to understand an idea, you have to be committed to this. If you want really to understand, because if you do what you do in stochastic analysis, somehow you study SDE and you learn think about the Markov process. You can do coupling and you prove convergence to equilibrium, and I mean, this paper of Funaki do this. I mean, he proved that here it's look at spin system. What he was looking, like Gibbs measure in infinite volume, and then he has the equilibrium dynamics, and then he proved that the Gibbs measure has decay of correlation by coupling of the dynamics. Okay, and so by a pathwise approach. So this is the kind of thing I want to do. And I mean, so far worked out relatively okay, it works. When you have convexity, you can do coupling and you can prove everything. When you don't have convexity, essentially it's difficult also to prove uniqueness, and you have a problem with uniqueness and with decay of correlation. This is the current status of the things. And then for 543, we don't have uniqueness. We don't have rotation invariance at the beginning. It's difficult to prove that you have rotation invariance at the end because of these facts. But yeah, and Parisi-Vu somehow this paper of these two papers of Chandra, Chevrier-Fayre, they understood how to do renormalization together with preserving gauge invariance. And this is so they end on the small scale. Now the challenging problem is how to globalize the results. So how you end on the large scale, okay? And that's difficult, and people know because essentially in the constructive, and this is what Balaban did for the measure, okay? So you have to do something for the equation, and it's not clear to me that that should be more difficult than what Balaban did, okay? Given the experience for 543, I don't see, because somehow Yang-Mills in 3 dimension, it's very subcritical. It's not as easy as 543, But okay, we have problem even with young means in 2 dimensions. Okay, this is, we already don't know how to do globally, so we don't have a complete stochastic quantization construction, but it's very subcritical, so it should be possible to do globalization of this of the solution. So I don't know how to do it, but okay, it's another problem. Okay. But there the problem are more geometric. So this is like people when they were studying, yeah, it's like when you study the heat flow of the Young-Mills equation, you have to be very smart, because if the equation is not linear, if you miss the structure of the equation, you cannot prove anything. And this is very tricky thing already for the Young-Mills flow. And this is more difficult, but okay, this is the interesting thing to do here. So how to globalize this recent result of Chandra-Chebyshев. I don't know if I answer your question, so somehow maybe I give more context, but
yeah, it wasn't really a well-posed question anyway. It was just more provocation. Anyway, well, if there are no further questions, thank you very much for this very nice talk, and yeah, thank you.
Yeah, no, thanks a lot. It was a pleasure to expose this here with a nice audience. Okay, so let me just make a small advertisement. So if you are curious about stochastic quantization and you want to understand without reading these 200 pages of paper, I think I gave a course in Milan 2 years ago. There are recording of video on YouTube, and there are my lecture notes somewhere on my website. And this is done for PhD students. So I try to be very pedagogical. No? So you can, I think the basic idea, these a priori estimates, is the control, how you prove this estimate for this moment estimate for the measure. These I try to explain there. Okay, so if you're curious, you can give a look. Okay, I think I hope to have made a reasonable. It's very elementary. There is nothing. It's all done in the on the lattice, infinite volume. But essentially, the idea is that okay, they want uniform estimate. How you get them there, and then you pass to the limit. Okay. So they are not all the detail, but I think the interesting ideas are there. Okay. By this I stop.
Hello, is it still possible to ask a question?
Yeah, sure.
Okay, so just it's a completely standard question which you must have been asked many times, but just maybe as an update from the last time it was discussed. So what are your feelings about the critical case, stochastic quantization of critical models?
Yes, so the problem. So in my group, we are making a bit of progress to understand. So we have to learn the renormalization group, made more systematic, and this we are doing, and we are learning a lot of things, and also thanks to this recent paper of Duch, which to me was somehow eye-opening, because I think there are very nice ideas there. And we are studying stochastic quantization of fermions, because we feel that for fermions it's easier to do this kind of things. So the critical case is still problematic, because people who try to do continuous renormalization group for fermion know already what is the problem. I don't want to do the discrete one because I don't like it, so I would like to do the continuous. But I guess that once some technical problems are understood, one should be able to do gross niveau in 2 dimensions in stochastic quantization, okay? Like you do for renormalization group. So at least for fermionic equation, I would guess one should be able to do it. And for bosonic equation, it's tricky. this question of coercivity. So this I don't know, but this is the problem of 544. Okay, these are what happens critically. But you see, we have really, I didn't talk about it, but we have stupid problems as SPD people. We don't know how to prove that supercritical SPD converges to Gaussian. Okay, this should be obvious. And this is a completely open, difficult problem in SPD, as far as I'm concerned. We don't know how to prove the KPZ in 3 dimensions converges to Gaussian. People do it, but using specific structure of KPZ. Okay, and if you understand renormalization group, you should say, okay, this is trivial. I mean, this is subcritical. Everything goes to 0. You should be able to prove that. When you rescale, so this is an infrared problem, okay? I'm not talking about the ultraviolet, okay? You take 545, imagine you have on the lattice, you have a large scale, then you rescale so that your observation scale is of order 1. And so the cutoff is going to 0, but then also the interaction is going to 0. And you should be able to prove that you converge to a Gaussian. And this is, I mean, people doing interaction particle system, they know how to do it for many interactive particles.
So if, say, even for the static problem, just 5, 4, 5 on the lattice, we only know it for small coupling constants that it goes to the free field. If you have large coupling constants, you can use reflection positivity to know it's Gaussian, but it's not known that's a free field.
Yeah. I am very imprecise, but you see, I don't know even for very small lambda. Okay, so you see, we don't know anything. I don't know how to prove it for small lambda. Yeah, I would agree with you that you would a priori not even know, even for KPZ. No, you don't expect for any lambda. You expect maybe that, I don't remember what happens, but maybe you expect that maybe there is, I mean, you cannot exclude there is a phase transition, no, because you go away, you maybe enter into the attraction point of some other fixed point, and then you are lost. But for some for small initial condition from the renormalization group, you should be still attracted to the Gaussian fixed point, and then you should be Gaussian. I hope actually that in the future we would be able to prove the existence of a trajectory near 4 dimension from below, like you do for the static problem. You see, for 5-4, for the fractional 5-4 problem. Yeah. So you see, this thing we are learning a bit how to do is still complicated. I mean, at this moment, we don't even know how to do uniqueness for 5-4. So you see, we are very, very far from acceptable.
When you say stochastic quantization for fermions, you've presented various different variants of what you call stochastic quantization.
Yeah.
The original Parisi-Vu-like, but then also towards the end, the variational principle, which had a scale decomposition.
Yeah.
And so that was a question I was wondering about. In what sense can you? So what kind of are you doing? You using a scale decomposition, I assume, or you?
Well, we looked for so the paper which are already almost published, because will appear soon in PTRF, is doing the parabolic approach. Okay.
Yeah, no, I was thinking the critical case, because for the critical case, it's not even. So if you just do the parabolic stochastic quantization, say, no,
I was thinking more about renormalization group kind.
Yeah, because then it's not even clear to me that that it exists in the same sense, right?
No, let's say, okay, let me make a small remark. For what we know about fermions is that we don't know at all how to renormalize equations. Okay, because as soon as you have, this is very difficult, because essentially you have to understand what are LP spaces for this, and we start to learn, but we put aside for a moment. It's complicated, it's non-commutative probability, it's very interesting, but it's not for now. we know now we shift the problem and we say, okay, let's try to understand renormalization group, because there we don't have a problem to renormalize the weak products, for example. And of course, the variational problem does not make sense, but the equation we have in the variational problem, the equation I showed you, this makes sense, okay? And we can prove, and we are writing this, and we wrote it down. We are writing a paper. I mean, it's not finished, it's on the way, but I think we can do all the subcritical problem. We are still not able to do the critical problem. Because, so critical, I don't even mean all the critical problem, okay? Gros-Neveu, Yukawa is not critical, but when you do with the renormalization group, is essentially as difficult as Gros-Neveu. It's not simpler, okay? So Yukawa formally, it's non-critical problem, but if you look at the work of Lesniewski, it's the same work, is exactly the same Gros-Neveu. So all you want to leverage that is asymptotically free, so the coupling is going to 0 anyway. So I think that you can handle asymptotically free. Okay, because you are using that it's going to 0, not as fast as the subcritical problem, but it's still good enough. It should be good enough for analysis to go on, but we don't know yet. I don't know. I think we have some hope. I mean, I don't want to claim right now, but maybe in 2 months I could claim that we can do all the subcritical problems. So this is the direction we are going now. And for the critical, actually, we have the problem. The problem we face is that I don't know how to implement. So I don't want to use these 3 formulas in the continuum. I don't know how to use it in the continuum, and somehow the technical problem is that when you do discrete renormalization group, you have this very effective 3 formula to control the combinatorics of the fermions. And we have a use of Pauli principle, but it's not as strong, and it's not clear to me why we are not able to do the same kind of estimate. So, okay, that's all for now.
In the critical case, as an alternative to Gros-Neveu, there are these models that your advisor introduced, these Caracciolo and so on, which I mean that's a it's well, anyway, we've looked at this, the continuum limit, but that would be very interesting. It's critical in 2 dimensions.
Yeah, but if they're critical, I mean, when I told Gros-Neveu is vague. It's like Giuliani. So it's these models where you have fermion. Actually, we don't even have fermion. We just have Grassmann, like symplectic, whatever. I don't know how you call it. There is no. We are not using in any relevant way the fact that you have a Dirac operator or things like this. Just that you have Grassmann, that you have a nonlinear interaction and things. So it could be anything, but if it's just critical, if you don't have this geometric gain when you try to do renormalization group equation, in the flow equation, if you don't have a geometric gain, then if you have only logarithmic gain, then we have to beat some combinatorial factor, and I don't know what to do. But for subcritical, essentially the combinatorial factor we got are killed by the decay and everything. It's fine. Yeah, but okay, this is a problem of us, which we are learning on the way, so little by little. And one day, yeah, I think it's even interesting. I mean, these spaces. Okay, sorry, I divagate here. Like stochastic analysis for fermions, like stochastic integral with Grassmann variable does not exist. I mean, it exists, this Russian did it, but in a very weak way. So you would like to introduce LP spaces that prove that the stochastic integral converge in LP and Ito formula is 6 and this kind of things, okay? All this does not exist yet. And it's difficult because non-commutative LP spaces are horrible to look at. Yeah, okay, so. Did you have any, did you have any news from Marchetti? You told me.
I don't know.